We could do that in C++, but what we need to do is to have separate swap function to be written for int, for float, for string, and so on, whatever type needs swapping. So we have to foresee and write that. But we cannot write a library function for swap, which will swap two values of the same type anyway. So that's where the template or the structural polymorphism parametrically comes into benefit. So we can say in an abstract form that if I have to swap x and y, then I'm swapping the two reference types of certain type t, and I have nothing to return, so I return a void. So if t is int, it will work for integer. If it is float, it will work for float, and so on. So that's the parameterization. So here I have a swap in the templatized parametric function form. Just for illustration, I'm showing another class here, int wrap, which is simply wrapping an integer. But once you wrap an integer, then naturally, in terms of type inferencing, it becomes a different type. So with this template declaration, you can, for these different variable declarations, you can define, you can invoke swap. And what swap does here, the resolution mechanism is, certainly it is polymorphic because you are being able to invoke the same function on different types, but you have not pre-decided it based, I mean, like in the overload resolution. But what the compiler does based on, suppose you have done swap CD for two variables C and D, which are double type. So what the compiler does, it automatically generates a swap function from this template for the double. So it has to deduce that T is a double, and then replace T in whole of this function signature and the function body. So this is easy because you know that two parameters both are of double. So C can work for X as an actual parameter if T were a double. Similarly, D can do that if for Y if T were a double. So you get a consistent set of equations, and you solve, you get T is double. So this will work. The other way, so this is what is called the implicit parameterization. You could also do explicit one. That is, you could instantiate with the type T. So this is the notation you must be familiar with. Swap, and within corner brackets, angle brackets, you write the type name. So it says that you generate a swap function replacing T by int. So this becomes a function available to the compiler. And then you try to do a basic function call matching for the function generated and the call here. So the call uses two int, and the function generated has two ints because T has been replaced by int. They match, so you call that function. Similarly, you will generate three other such swap functions. So you are, by explicit parameterization, you are actually putting it in the domain of overloading. So in effect, you have four functions generated from this template, and these four functions will be resolved based on their parameter type, which is certainly resolving that T is such and such and so on. Now let us try to see something. I mean, will it work for every type? Will this swap function work for every type? For example, let's say I have two variables, Ci and Di, which are const int. So swap Ci, Di we do. Again, the solver will tell you T is const int. So that part is fine. Now, when you actually look at the body, now what you'll have const int temp being assigned a value X, which is also constant. Now, this is initialization, so this part will work. This is not a problem. But then you have Y being assigned to X. Y is a constant, that is fine, it can be on the R value. it's a constant. So this assignment will not work. So the compiler will fail because constant cannot be assigned. So what we learn here is while a basic parametric mechanism could work for several types, but the type that you resolve or the type that you get from the solver, you produce from the solver, has to have certain properties. And these are called type traits. So the trait required here for T, at least 3 traits you can easily see in this code. One is I'm constructing an object of type T. So it must have a constructor which is available. Second, it is making an assignment. So copy assignment operator must be possible. And third, obviously at the end of this function scope, this temporary variable will be destroyed. So the destructor must be available, right? So these 3 traits are very obvious from the swap function that we have written. So if you instantiate it by const int, it will not compile because const int cannot have a copy assignment operator, and you will get a compilation error here. Suppose you try to do a mixed mode, that int I double D, and you try to do a swap. Now your solver is in a problem because I being int tells you that T has to be int. D being double tells you that T has to be double. So T has 2 possible solutions, not a single consistent solution that you can say T would take. So the compiler will not be able to generate an appropriate swap function for this call, and it will say that the template parameter T is ambiguous. I'm taking a very simple example, but that is a crux of how things work in the type system. Okay, to take care of this, I might want to use an explicit parameterization. I say swap double and put ij. So if I say swap double, then I am explicitly said that T is double. So now what I have a function which is swap of 2 double variables declared, and I'm calling it with int. Now this is where the additional fun begins. Is if you had done it in terms of a normal call, then this would have gone through, because you can actually implicitly convert an integer value to a double. So you have, as if declared a swap function with 2 double variables, reference to 2 double variables, and you can call them with integer because your implicit conversion it will work. But in this case it will not, because when you use templatized function, the mechanism of implicit conversion is kept it's kept aside. It will, after this typification through the parameter type resolution, it has to exactly match the type. Otherwise the template call will, so template call will not let implicit conversion to happen. That's kind of the type system rule that it does. So therefore it will say that you cannot convert parameter 1 from int to double, right? It's same thing is for parameter 2 as well. So this is the basic parametric polymorphism that we have. And so we can see that we have a swap function which is generic, but it has certain restrictions, and certain calls are getting, like the call with const int certainly is not meaningful, but the other 2 calls are meaningful, but that will not go through this definition. Let's see another way into this problem. Look into an interesting definition. I have defined a class uncopyable with a protected member function, which is the overload of copy assignment operator, right? So it is, the signature is correct, and it is just put there. And then I have derived my class from this uncopyable int wrap. So what do I mean? What I mean that uncopyable is a base class, and int wrap is a specialization of that. So int wrap will inherit the uncopyable copy assignment operator, and because it is protected, so the base class will inherit that, which means that int wrap now will not have a free copy assignment operator that the compiler can provide, right? So you need to now provide an interrupt one. So then with this, you call this swap function. You have two interrupt variables A and B, and you call swap AB. So this will immediately deduce that T is interrupt. Or you do an explicit parameterization and you call, with that you call AB. So in either case, a swap function with interrupt as T will get generated. But as it gets generated, it will know that it has a copy assignment operator in interrupt, which is this function inherited from here. So that is what will be used in case of x assigned y or temp assigned y, right? But then it will need that function to be given. So this function is defined because you have given the signature. This member function is there. You have overloaded. But you have not provided a body of this function. You have not given the definition for how the uncopyable copy assignment operator will work, right? But because you have done this derivation from uncopyable, you have not allowed the compiler also to give a free copy assignment. So what it says that x assigned y will be x dot operator copy assignment, which is actually of the uncopyable. So it is x dot uncopyable colon colon operator copy assignment taking y as a parameter. That function does not have a body. So the compiler will go through fine because compiler has found the function, but the linker will have a problem because you have not actually defined. The linker needs to link between a call and the actual function body, which is not there. So the linker says in both cases that unresolved external parameter, this whole signature, right? So these are cases where a type cannot be used in terms of a template parameter type for a function like swap. So this is just another way of looking at it, that it's not only in terms of constness that you can violate, but it could be in terms of your design that you could restrict something from being copyable, and therefore application of functions like swap will not work. Now let us move on. Let's take another two parameter function, say add. Right. So I have a template T, a template add. I have two parameters A and B of the same type. It returns A plus B. And unlike swap, now I have a return type. And the return type will be the same type as the parameters, right? So what will this need? This will need, you are adding A with B in type T. So in type T, it needs a overload of the operator plus. So that is what the type system will need to map it to. That is A dot operator plus B, or some global function operator plus for that type T, which can access the internals of the type, right? So either of that will be required. So that is the trait information is certainly here. Then you are returning by value because this is just type T. So you will need a copy constructor to actually return this value, because you will need to construct the return value, right? So this is the basic trait. Now I provide the interrupt operator plus overload as a friend function here, which is a simple thing. And I have used the constructor here. I have not given a separate copy constructor. I will let the compiler's free copy constructor to be used for returning, because I just have a single value. So bit copy will work here as a pretty, that bit copy, the shallow copy will work in this case. Okay. Now, if we look in terms of the typed lambda calculus, this is what we have. And the type system of a typed lambda calculus will easily deduce this type. That is, if A is of type T and B is of type T, then you do A plus B. So T is the type variable that engages here. Again, look at different calls. The first 4 calls are implicit, in which case both parameters have the same type and the type will get deduced. I can explicitly type this template and instantiate. So I will use that. Now let us look at what happens in mixed mode. Suppose I do add IDE. I is integer, D is double. So now my type system cannot resolve T, because one says it is int, the other says it is double. The same kind of issue we are seeing for swap. Similarly, if we just put a different order, DI, the same thing will happen. If I put it to int, if I explicitly say it is int, then T is int. But that means that yeah, I have a function generated for add which takes 2 ints and returns an int. But I'm calling it with an int and a double. Right? So that needs an implicit conversion, so which is not allowed in template instantiation. So it will say that no instance of template function matches this. Similar thing will happen if I have it for double as well. So if I say it is double, then again it will say that I have a double. I'm trying to call this with an int which is not convertible. Right? So this is the kind of problem that you will get in terms of parametric polymorphism. So given, the polymorphism structurally says that I have values of the same type and I will return a value of that type as well. But your call is not conforming to that. None of these are. So none of these actually work. So we need to improve on that. So we improve, what we say is we do a, let's say we do a template now with 2 parameters, T1 and T2. I say 2 parameters can be of 2 types. So T1 and T2, and I do a add of them. So operator overloading is required here for this purpose. So it is it is to be done for the two types now, and it returns the type of the first parameter type. That is what we have said. And intrap, the operator plus in intrap is overloaded through a friend function. So I have here the implicit parameterized calls. All of them will work because what I'm doing is I'm converting from I'm solving the equation that int is I goes for A, so I has a type int, so T1 is int. J has a type J goes for B, so it is int, so T2 should be int. So T1, T2 both should be int, and their result should be the int as well. Similarly with doubles, it will have that with string. So the same types for both T1, T2, it will work as before. Now what will happen if we have a mixed mode? If we have a mixed mode, now we have int and double being sent. So T1 is int, T2 is double, and the return value is of int, right? So now in terms of the function call, you do not need any implicit conversion. So this is perfectly okay now with the template to call this function because you have a perfect type matching here. Int with int, double with double, ID. But the value that you will compute out of here is naturally the addition of int with double, which produces a double. And T1, your declared return type is int. So this needs a conversion from double to int. This does not prohibit parametric function call because that resolution is in terms of the parameter types, not in terms of the return type. So this will give you a warning that return converts from double to int, right? So, but it will still work. The compiler will say, okay, something is, type system says, okay, something is wrong. You are converting from double to int, you might lose information. But if you call it as, simple thing, this particular template has made the add function asymmetric, you can see, because if you just change the order of the parameters, you make it di, then T1 is resolved as double and T2 as int. So the return type now is double. So the result computed is actually int, because it's actually double. No, I'm sorry. It's actually double because int plus double, the mixed mode normal rule. And you are returning that double. So there is no problem in terms of this. So this call will go through without any warning. So this is kind of the way you can, I mean, the type system handles mixed mode in the function. Okay. Now, to get rid of that warning, because I should be able to say what is the return type. So let me try to put a third parameter. The third parameter is basically the, one second. So I'm sorry. So the third parameter R is specified. So if you look at the lambda expression, then I have A of T1, B of T2, and R of R, and I'm doing A plus B. Right. So T1, T2, and R are type variables. And there are several single mode or mixed mode calls given. But the problem in all of these is that you have resolutions for T1 and T2 in every case, whether it is single mode or it is mixed mode. But you have no resolution for R. The type system cannot resolve R because from the call, you do not know what is the type that must be returned. Right? So that is the limitation of the type system. It cannot. You can look at the lambda expression. If you try to find a type for this, you will still not be able to resolve for R. Right? So this again, this attempt to specify the type of the return type will not work in any implicit call. So to make it work, what you'll need to do, I'm in slide 81 now. What you need to make it is that you specify explicitly all the types. That as you are saying the parameter types, you also say what is the return type. So you say the return type is, so you say int, 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 double, 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 like that. So you are explicitly saying that, or you are saying here in a mixed mode, you are saying int double, double. So you know that return type is double. You are saying double int double. So you know the return type is double again. And therefore, since you have explicitly specified, the R does not need to be resolved. T1, T2, R all are given. So from that, the compiler knows what type of function signature to, what type of function to generate. And there is no implicit conversion required anymore because you are clearly saying that the return type is double. So all of these will compile without any problem. So they will work perfectly. But the flip side is now you have lost the whole beauty of polymorphism, because you are being relieved from not writing so many different functions which you would have required. If you would have done just ad hoc polymorphism of overload, you would have required to write these 6 functions, which you don't need to write anymore, because all of them are getting generated through parameterization. But you still need to instantiate them through explicit parameterization, which loses the whole beauty of the language. You would like to just still call them as add, right? So this is something which is supported through partial template specialization. Right. So this is another parametric feature, is that if you have templatized functions, this is the basic function. Now I say that I have now a overload of this template where I have replaced R by T1. Then I have another overload of this template where I've replaced T1, T2, R, all of them by T. So these two are the earliest signatures that we had written in order to write a add function. This is called partial template specialization. Why partial? Because it has some template having 3 parameters, and some of them, like in the first case, R I have actually specialized. I have made R as T1. So it is partial, but all have not been done. So here, R T1, R and T2 are specialized. So this is partially being specialized. And then I say that, well, I can actually specialize everything and say that this is the default int function. Right? R, T1, T2 are all are int. Right? And then I provide int wrap here just for illustration. Now what happens is, if I do add ij, then what are the possibilities? That can be any one of these, right? It can be this function add, which is for int. This can solve t for int, can take this. It can solve t1 for int and t2 for int, can take this. It cannot solve for the general template. Now, if you have this situation, then the type system goes by the rule that something that needs the minimal specialization, minimal solving, is the function. So this has a best match with this function, which is fully specialized. But if you call it for double, there is no such function for double, for add. So it takes both of them as double. So it matches this fn1, because t will be solved for double and this will match. It can also match for the second, fn2, which is t1 is double and t2 is double, but between these two it will choose this one because this needs a less specialization. So all of this double string int wrap will call this first signature fn1. If you do a mixed mode between them, id and di, then it has 2 parameters which are not resolved, t1 and t2. So it will allow these calls to go through as fn2. Of course, it will have that warning problem, as we have seen. When we do this, it will first, particularly when I do add id, it has a return type which is int from a computed double data, and therefore it will have that warning problem, but this will also work. And finally, I can actually fully specialize by giving all these parameters when I want that, well, I really do not want to create any confusion. I will explicitly say what I'm doing. Then I give a fully specialized parameter template instantiation, and that will call F3 without any wording or anything, right? So with the template specialization, you can see partial template specialization, you can enable the type system to actually create a set of add functions which will work for all your scenarios. That if you have something special to add, for example, I could say that instead of string, suppose you want to define an add function for char star pointers, right? In terms of char star pointer, you do not have an addition operator, right? Naturally, adding 2 pointers does not make sense. So, but what you want to mean is a char star pointer is a C style string. So when you want to do add of 2 char star pointers, actually you want to do a concatenation of the C style strings and return a char star pointer to the resultant string. So you could do and in the body, you could actually do all that is required for concatenating 2 strings and returning a result string. Otherwise, you can see that in any of this specialization, we have actually in turn always instantiated the parameter, the first function. One second. 1 second. Okay, sorry. So this is, so you can see, you can get a good view of the, parametric polymorphism and how type systems in language like C++ would be able to handle that and deduce proper type from the structural definition of the add function. Right. So this is something which is very powerful and which we otherwise call template meta programming, or we call generic programming that you have. So let me stop at this point, and because this is something very, very critical in terms of the type system, and see if you have any questions. Any questions, friends? Okay, no. So let's proceed. So I hope you understand this, and if you are not familiar with this kind of template programming in C++, just try out a quick set of examples and get confident, because in terms of type inferencing and reduction, both the way the ad hoc polymorphism is resolved and the way the parametric polymorphism is resolved are core to type systems beyond the basic type matching and type inferencing processes, right? So let me just give you a quick overview of the whole scenario that it starts now. So we are doing various kinds of type declarations, and we need to deduce the type equality to infer whether two variables or two expressions are of the same type. So when we declare a type name, it is important to decide whether it is a new type that is different from all other types that you already have in the system, or it is a new name whose meaning is equal to some other type which is used in elsewhere in the program, right? So type name, using a type name, will always have that. And programming languages have complicated forms in the type system for equality, and which lead to confusing forms of type declaration. But there are two simple rules, that the type systems use. One is called transparent declaration, and the other is called opaque declaration, right? So I've just given examples to show you. From this example actually can exist in C as well, so it's just extended from C. So type def does not actually define a type. It defines a alias, a second name to the existing type. So I can say type def int a. So I'm giving a type name a to the type int. I can do type def int b. I'm giving a separate name b to the type int. And then I can use to declare variables like this. Variable a is of type cap a, variable b is of type cap b, and there's a variable c which is int. The question is, will these a, b, c be considered to be of the same type or of different types? Now, in this case of a simple int, or pre-declared, pre-defined types, C++ type system follows a transparent rule. That is, if they are type deft to the same type, they are also the same type. So you can assign A to B to A, even though they look to be of different types, but they name the same type. So you can assign C to B, though C is directly int, B is type deft as in, right? Which is logical, right? But very interestingly, a opaque system is where you give a name and that name introduces a new type. In the previous case, you have given an alternate name to an existing type, but here you are giving a name to a new type. And yes, see, very interestingly, you have a struct which is just wrapping an int, right? One field. And you have another struct which is wrapping an int. So if you look at structurally, without this type def, you will say they are the same type, because both of them are structure of an int data member. In fact, that name of that data member is also kept to be same, right? So they should be. Now you type def to x and y. Let us define two variables, x and x1 for type x and variable y for type y. Now, if you assign x1 to x, this is compatible. This is considered compatible. That is, you can make this assignment. You can take two structures of type x and assign. But you cannot assign y to x. This is considered incompatible, even though x and y structurally are the same type. But what happens in terms of the type system of C, C++, the moment you define a structure, the same thing will happen for class, of course. The moment you define a structure, you necessarily defining a new type. So two classes or structures will never be compared for their actual structure, for their actual data members or other members. The moment you declare one, it is a different type. So that is the opacity of the system. So in the first case, we saw the transparency of the system. In the second, we saw the opacity of the system. And different languages might use different transparency or opacity rules for the type system. But this is in C++, the transparency applies to predefined types, and opacity applies to any type that you build up. Right? So this is the basic forms of equivalence that you work on. Now, based on this, if we try to look at the type compatibility, how it plays to polymorphism, we will see that naturally type compatibility is the heart of polymorphism, because polymorphism is you have an object of a certain type and you are using it in the context of a different type. That is polymorphism, right? Or multiple objects of different types you are using in the same context of a type. So to be able to use that, you need to have this compatibility rules. That is what all that we were looking at through the swap and add examples. So so types are in this way. I mean, the same thing happens for a subtype supertype relationship also. A subtype is compatible with a supertype, right? But two classes not on a not on a hierarchy are considered to be unrelated types, and they are not compatible. So we have primarily two forms of type compatibility. One is called nominative and the other is called structural. A nominative compatibility is when two variables are type compatible if and only if their declarations name the same type, like in type def. Two variables are of that same type. In a nominative subtyping, such as inheritance in C++, supertype subtype relationships are explicitly declared. Right. So this is, if you think of it, nominative compatibility is primarily the ad hoc polymorphism. Significantly, much of the ad hoc polymorphism, including the subtype polymorphism and most of the quotient polymorphism that we are talking of. But there is another, which is structural compatibility, is what we were looking at in terms of the add function, where two type equivalence is determined by the type's actual structure or definition. Like we had one definition for that, and then multiple forms, multiple interfaces to actually instantiate it. So structurally, it is the same structure, but it is being used in the context of variety of different types. So unlike nominative compatibility, where since the declared type names have to be same or related in supertype subtype relationship, in structural compatibility, you could actually apply to completely unexpected unknown types. When you are writing the signature for swap or add, you just do not know what type they will be used for, right? So, for example, let's consider an example here. You have a dog class, you have a cat class. The dog class has a member which which gives you a name, right? It's a const member function and gives you a reference to a const name and string name, const string. And then you have a move to function. A dog can move to a certain point, right? So you have some point class. I mean, we are not going into the details of compilable declaration, but we are just conceptually looking at a dog can move there. Now, from this conceptual commonality, I have a cat defined here. So if you look at, except for the name dog and cat, they are of the same structure, right? Because both have name, both can move to, and these signatures are same. These member signatures are same. In fact, you can have a class which is called things with name, something which has name. So actually, these could be in a structural system. Things with name is a super type for dog and cat, but in a nominative system, both, even though cat and dog have the same structure, they are not considered equivalent nominative types. They cannot be considered. So you cannot use dog in place of cat or vice versa, right? So that's the basic difference. So if I apply a ad hoc polymorphism on this dog and cat, and I want to now write a print function, print name function for them. So I will write a print name function which does this, which is print name, takes the reference to a constant dog object and does the printing, right? It uses the name method. I give a print function, print name for cat, which does the same thing. Then I can instantiate dog, instantiate cat, print their names. And what I'm doing is I'm actually writing the same function multiple times for these different dog and cat classes, because I'm using a nominative compatibility. And in a nominative way, print name here and print name here are different because they refer to two different types, right? So in a more generic system, this is a scope. I mean, even with the polymorphism which allow me to have the same name and therefore relieves me from really remembering that what is the print name of dog function, print name function of the dog is, or print name function of the cat is. I can use the same function, but it still needs, it has a lot of code repetition, because all of these are structurally the same function. I can now put this in terms of a structural polymorphism by defining a template on print name and write this function there. And then I do this. What happens is when I do print name D, it resolves that D is of type dog and creates this function that I had to write at the beginning for ad hoc polymorphism. So these functions get automatically generated because they have the same structure. Now you see that print name does not know anything about dog or cat. It just knows that it gets a variable, v, a constant reference to a variable v of some type which has a name method, and it has to print that name method. So conceptually, it gives you a whole lot of code reuse option, and then based on the actual ad hoc type, the nominative type, the structural definition gets used. So this is the basic difference between the nominative and structural compatibility. Actually, there is a very interesting design pattern known as curiously recurring template pattern, which use templates and inheritance to simulate subtype polymorphism at compile time. Subtype polymorphism happens at the runtime. We know, because that's a dynamic one. But you could simulate something similar, and I use the dog cat example to illustrate. So you have an animal which is the base type. So it has a get name, so that you can get the name of this. And how does it get the name? It basically takes the type T and converts this pointer to a const T star pointer and calls the name on that after the static cast. Now you specialize dog from animal using dog as the instantiable type for T, right? So this is the recurring part. So you are specializing from animal, which is a structurally generic type, and you are specializing that into a base type, which is animal dog, and and deriving from that. So here T is dog, and dog now has this get name through this function. Cat similarly can be specialized, and then I write a generic print name template using this get name. So you can see that here if you are doing print name on D, it will get dispatched to the print name here, which is to do get name. And it will do get name for what? Because it will use the animal dog. So it will come here, but do it for the animal dog. So this kind of, so you're actually calling a base class function from which you have specialized, which is the subtype, which does the subtype polymorphism do, that you call the base class function and it gets dispatched to the proper derived class. But here you are being able to do that at the compile time. Of course, you'll be able to do that if you know this type at the compile time, the type of D at the compile time. Otherwise, you need to come to naturally the subtype polymorphism in the ad hoc scheme. But this shows that this particular pattern shows that there are very interesting mix between nominative and structural compatibility that can be done. So this is what I wanted to talk of today. We will talk more about things in C++11. We have run out of time today. Is there any question I can quickly take? Otherwise, any question, friends? No, I just hope you are following this, because type system is something which is very, very critical in terms of any programming language. And what I am, since it is so complex, what I'm trying to do is, besides giving you the formal background of the type system in terms of type lambda calculus, I'm trying to show you that in a practical programming language, what are the considerations and strategies that the type system has to follow. So please, I mean, go through this. I will share this presentation, go through, and in the next class, if you think, if you have any question, please ask me. Have a nice day, and let me stop here. We'll meet on Wednesday.